Space fans are eagerly counting down to Starship's fifth flight, as the goal this time is incredibly ambitious, a perfect soft landing of the ship. To accomplish this, the thermal protection system must perform flawlessly, and that's why SpaceX has unleashed revolutionary solutions for the TPS. So, what upgrades have they made, and how do they help? Before we find out the answers, don't forget to subscribe and hit the like button to stay updated. Alright, let's dive right in. During the fourth flight, the heat shield did an outstanding job protecting Starship until the very last moment. However, there's still so much room for improvement. Despite their heroic performance, the thermal tiles couldn't completely withstand the harsh conditions, many tiles detaching during re-entry. Each flash of light seemed to mark a failing tile. Although S-29 landed successfully, this issue remains a major challenge for future missions. In typical SpaceX fashion, a bold solution was promptly proposed. Just 4 days after the fourth flight, Elon Musk announced on X the replacement of the heat shield with tiles twice as strong. Additionally, an ablative layer underneath would serve as a secondary thermal barrier. Right after that, a massive TPS overhaul ensued immediately. Dozens of scaffolds were erected, and engineers wasted no time in removing the old heat shield, replacing it with new tile. With around 18,000 tiles to replace and the work still needing to be done manually, this was truly an extraordinary effort. So, what makes these new tiles stronger? The secret behind their doubled strength lies in their microstructure. Take a look at this image of a standard heat shield tile under a microscope. You can see a very complex fiber structure, hinting at potential materials like silica, alumina borosilicate, and aluminum oxide fibers. To make the tile material stronger, SpaceX likely reinforced it by adding thicker aluminum oxide fibers into the mix. These fibers could increase the weight of each tile by about 10%, but in return, they offer exceptional heat resistance and pressure endurance, maintaining performance under extreme conditions. But that's not all. SpaceX also boldly upgraded its secondary thermal protection layer. The previous thermal blanket, thought to be cow wool, has been replaced with an ablative material, a well-known one in the aerospace industry. SpaceX is no stranger to this technology, as their Dragon spacecraft uses a similar material, specifically the Pica X heat shield. This combination creates a multi-layered defense, ensuring the ship's safety during re-entry. They say it, they do it. By the 15th of this month, Ship 30 was spotted with only a few spots left and tiled on the nose cone and flap. And just a few days later, the process was 100% complete. Lightning fast. Now, let's talk about controlling deceleration and heat dissipation. To do that, a spacecraft needs to control its angle of attack. Starship needs to maintain a 60-degree angle of attack. Sound familiar? The Space Shuttle used its wings to maintain a 40-degree angle, while standard capsules like Orion control their 60-degree angle by moving their center of mass off-axis. This is when the flaps take center stage. And that's another issue SpaceX had to solve, one that caught all our attention: the forward flap. Remember the incident with the forward flap? A few heat shield tiles around the flap hinge area failed, with plasma hot enough to melt metal, piercing through the hinge gap and nearly tearing the flap apart. Luckily, Starship held strong, maintaining a relatively stable angle of attack and guiding itself to a soft ocean landing. Though it missed the target by 6 kilometers, it was still a spectacular victory. Alright, let's see how SpaceX plans to handle this issue. They have a bold plan: move the flaps to a more wind-sheltered position to protect the hinges from that terrible plasma flow, while also creating a gas shield to protect the hinge. Sounds cool, doesn't it? But you know what? Before Flight 4 took place, Elon Musk had predicted that the flaps would be Starship's weak point during atmospheric re-entry. And here's the interesting part. Musk and his team had anticipated this 3 years ago. Don't believe it? Look, here's his tweet about Starship's flaps from 2021. BTW, there's a slight error with forward flap design. Moving section is needed for control, but passive section is counterproductive, as it pushes nose backwards. And you know what? These are exactly the adjustments we see in the newly emerged Starship V2 flap design. So, why hasn't the forward flap design changed over the past 3 years? This flap design has been around for 4 years, starting with the first completed prototype, SN8. The answer lies in SpaceX's rapid iteration strategy. They build many ships in a short time to serve their tests. Therefore, they will keep this flap design for another 1 or 2 flights to gather the necessary data and then leap straight to Starship V2 with a more efficient flap design. The TPS has been updated, and on July 27, 2024, Ship 30 completed its static fire test. During this process, Starship had to endure intense vibrations from the Raptor engines. Initially, 3 vacuum engines were activated, followed by all 6 engines firing up, creating immense tremors. However, what's truly astounding is that the thermal tiles remained firmly attached to the ship's body, without falling off. This is a remarkable testament to the durability and effectiveness of Starship's thermal protection system. You see, both stages of Flight 5 have completed their static fire tests. This means we are getting closer to being ready for Flight 5, which has incredibly ambitious goals. Success rate? Hard to predict, but with the new improvements, hopes are very high. So, how much of a success rate do you give Flight 5? Comment below. I'm personally very optimistic about the upcoming launch, and I believe that Starship's TPS will perform excellently this time around. And there's a good reason for that. This system is even more advanced than the Space Shuttle's TPS, a technological marvel of the past. In fact, you could call Starship's thermal tiles a legacy of the Space Shuttle. As I mentioned earlier, when analyzing the material structure, we see similarities between Starship's thermal tiles and the AETB, a material with a 2Phi coating and molybdenum disilicide additions, which were crucial in the final years of the Space Shuttle program. Moreover, structurally, the Space Shuttle's thermal tiles were known for their outer coating of tetrasilicide and borosilicate glass. Similarly, Starship's thermal tiles have a distinctive black color. When observing Starship during re-entry, you'll notice a beautiful blue glow of plasma surrounding it. This indicates that SpaceX might be using a similar borosilicate coating, as borosilicate burns with a blue flame. However, the Space Shuttle was an engineering masterpiece from decades ago. Its thermal protection system, though advanced for its time, had weaknesses that do not align with Starship's ambitious goals today. The orbiter's complex shape meant that most of its 24,000 tiles were unique in size and shape, making production, quality control, and refurbishment a logistical nightmare. The orbiter's TPS wasn't a simple system, but a collection of heat-resistant materials, each carefully selected for specific areas of the spacecraft. For instance, reinforced carbon-carbon, RCC, could withstand re-entry temperatures up to 1260 degrees, protecting the nose and leading edges. High-temperature reusable surface insulation, HRSI tiles, made from Li900 silica ceramics with a heat-resistant coating, were used on the underside where temperatures were lower. Felt reusable surface insulation, FRSI, provided protection for areas with temperatures below 371 degrees Celsius. In the past, maintaining the Space Shuttle's TPS required up to 80,000 work hours between flights, including inspections, repairs, waterproofing, and recertification. In contrast, Starship aims for a turnaround time of just about an hour, without needing such extensive labor. Starship's thermal tiles are designed with nearly uniform size and thickness across the entire spacecraft. Only about 100 tiles have special shapes for areas like the nose and corners. While this might slightly increase the overall weight of the spacecraft, it offers significant benefits in production, maintenance, and repair. This uniformity allows for complete automation in manufacturing and quality control processes, leading to simpler construction, shorter production times, significantly reduced costs, and increased reliability. This is a prime example of how simple design can yield immense benefits in space exploration, embodying the less complexity, more efficiency philosophy in modern aerospace engineering. A critical weakness of the Space Shuttle's thermal protection system lay in its aluminum structural frame. Although aluminum melts at around 660 degrees Celsius, its mechanical properties begin to degrade at much lower temperatures. At around 250 degrees Celsius, aluminum loses a significant portion of its strength and rigidity, severely compromising the spacecraft's structural integrity. This is why I say that choosing stainless steel, contrary to the trend of using carbon fiber and aluminum as primary materials, was an incredibly wise decision by Elon Musk. The method of attaching thermal tiles is also a crucial difference. The Space Shuttle used adhesive to secure its tiles. However, adhesives and the underlying aluminum structure couldn't withstand extremely high temperatures, necessitating the use of thick and heavy tiles, which increased the spacecraft's overall weight. In contrast, Starship employs an advanced method using smooth pins to mechanically secure the tiles to the ship's body. This method is so robust that under normal conditions, removing a tile without breaking it is nearly impossible. Moreover, you can easily see which one has the advantage just from their appearance. Specifically, the Starship has a simple cone and cylinder fuselage, a unique canard tailless aerodynamic layout for re-entry flight, and heat protection tiles on the windward side to cope with the thermal environment of re-entry. It's clear that the current aerodynamic layout of the Starship differs from both traditional crewed capsule, the Space Shuttle, the Radical Aerospace plane, and even earlier configurations of BFR. The simple shape of a symmetric cone-column wing combination is intuitively convenient for a clean two-stage rocket configuration, in tandem with a super-heavy booster of the same diameter. This setup is much simpler than the complex orbiter-fueled tank booster parallel layout of the Space Shuttle. The corresponding active segment aerodynamic characteristics, flight control, and booster separation design are also much simpler. But that's not all. The blunt shape of Starship is not just an aesthetic choice. It's a sophisticated aerodynamic strategy. As Starship hurtles into the atmosphere at supersonic speeds, its blunt shape creates a strong compression zone. The temperature in this zone spikes significantly, but it also creates a thermal gradient, with temperatures decreasing toward the rear. This mechanism acts as a natural aerodynamic heat shield, protecting the spacecraft's main structure from the extreme heat. This efficient heat dissipation capability of the blunt vehicle shape surpasses the wing design of the Space Shuttle. Overall, Starship's aerodynamic configuration has clear mission requirements and design objectives. Avoiding unfavorable small angle of attack conditions and flying at advantageous large angles of attack, Starship adopts a simple tailless design. This not only meets stability requirements, but also simplifies the aerodynamic, structural, and thermal design, reducing weight and achieving overall optimization. This is a very neat and reasonable design solution. Bringing a massive structure like a spaceship back to Earth safely is nothing short of an art. SpaceX has meticulously considered what they need to do with Starship's TPS. They've not only learned from the past, but also know how to avoid repeating old mistakes. It's like learning from others' experiences to perfect their own. With these bold upgrades to the TPS, I'm confident that Starship will splash down in the ocean perfectly, and it won't be long before we see it smoothly landing on solid ground as well. All right, that's it for today. Thanks for watching, and we'll see you next time.